Welcome everybody to the presentation about our paper Reinforced Particle Bed Printing by combination of the selective paste intrusion method with wire and arc additive manufacturing, a first feasibility study. This paper is a result of a cooperation between the Chair of Machine Tools and Manufacturing Technology, represented by Daniel Baier, Sophia Prottung, Andreas Bachmann and Michael Zäh, and the Chair of Material Science and Testing, represented by Alexander Straßer, Thomas Kränkel, Christoph Gehlen and myself. This paper presents first results of an ongoing research project with the goal of implementing reinforcement with wire and arc additive manufacturing in concrete elements produced by the selective paste intrusion method. On the left side, you can see a scene of the selective paste intrusion production process where the nozzle applies the cement paste to bind a layer of aggregates in the particle bed, and the advantages of SPI structures are the high compressive strength with over 78 megapascal after 7 days and the high durability. The helix in the middle exhibits which complex structures can be made by the selective paste intrusion process, and the wall thickness here is 1 centimeter. On the right side is a picture taken during the wire and arc additive manufacturing process where the welding head deposits the electrode on the substrate. Next to it is a picture that shows the ability of overhanging structures which can be produced with this technique. These examples show that the combination of these two techniques enables a load path optimized construction of reinforced structures and new ways of saving building material. Now let's have a look at how to combine these two processes. In the first step, a couple of centimeters of wire and arc additive manufactured reinforcement will be pre-produced. In the second step, a first layer of aggregate is spread, and due to the permeability, the grains fold around the wire and arc additive manufactured reinforcement. However, even after the application of the aggregates, there is still a space between the head of the reinforcement and the surface of the particle bed. Why we need the space between the welding spot and the particle bed, I will explain in the next slides. In the third step, cement paste is applied to bind those areas where the specimen shall be produced. Then the steps of application of the next layer of steel, aggregates and cement paste are repeated until the structure is finished. In the last step, the structure becomes excavated. This method allows the production of more complex structures as it is possible with extrusion techniques due to the supporting ability of the surrounding non-bond particles. The main challenge of the combination of these two methods are the high temperatures with more than 1500 degrees Celsius at the welding spot. Therefore, this feasibility study was done to check if it is even possible to use these two methods simultaneously. The overall goal of the research project are to minimize the heat transfer and propagation into the particle bed and to adapt the particles of the cement paste to withstand the remaining thermal load. Therefore, two experiments were done for this feasibility study. The first is to determine the rheological behavior of cement paste depending on temperature. To know that behavior is important because the rheology of the cement paste is crucial for the penetration ability and therefore the layer bonding strength and durability and shape accuracy. In this first experiment, two very fluid mixtures with a mini slump flow of about 400 millimeters were tested. The water-cement ratio of the mixtures was fixed to 0.3, and for the measurements, two mixtures were produced with varying cement and superplasticizer type. There, mixture 1 consisted of a normal OPC, and mixture 2 was made of a rapid OPC. And comparing the two superplasticizers, superplasticizer A should show a slow absorption behavior and liquefaction over the time, whereas superplasticizer B should absorb faster but with decreasing effectivity over time. We measured the rheological properties with a double plate geometry with a descending step profile at temperatures between 20 degrees Celsius and 70 degrees Celsius in increments of 10 degrees. The yield stress and the apparent viscosity were determined using the Herschel-Buckley model, and each measurement was done 15 minutes after addition of water. Now let's have a look at the results of the measurements of mixture 1 on the left and mixture 2 on the right. The diagrams show the yield stress in dotted lines and the apparent viscosity between a shear rate of 0.1 and 10. The literature mentions the shear rates as the appearing shear rates during the penetration of cement paste under gravity in the particle bed. For both mixtures, we can see an increase in yield stress due to the increased hydration kinetics with temperature. However, due to the faster absorption ability of superplasticizer B, mixture 2 can counteract the accelerated hydration kinetics until 40 degrees Celsius. But yield stress increases a lot at 60 degrees Celsius. Whereas the yield stress of mixture 1 constantly increases very little from only 1.4 Pascal to 1.n Pascal between 20 degrees Celsius and 40 degrees Celsius, but does not show the strong increase for higher temperatures. For evaluation of these results, it's good to know that yield stress of the cement paste should be smaller than 3 to 6 Pascal to achieve sufficient penetration behavior. But this value depends on the grain size of the particle bed. Looking at the measurements of the apparent viscosity, the results exhibit a decrease of the apparent viscosity for both mixtures between 20 degrees Celsius and 70 degrees Celsius. Experiments showed that a low apparent viscosity is beneficial for the penetration ability of the cement paste in the particle bed. One possible explanation for this, beside others, is that the increasing absorption behavior of the superplasticizers with increasing temperature. Now let's have a short conclusion of the results of the rheological measurements. So both cement paste mixtures can be used up to a temperature of 50 degrees Celsius with sufficient rheological properties, and mixture 1 was even usable up to 70 degrees Celsius. However, the evaporation of the water from the cement paste at increased temperatures has to be considered in further investigations. The apparent viscosity between a shear rate of 0.1 and 10 decreased for both mixtures with increasing temperatures up to 70 degrees Celsius, which is advantageous for the penetration behavior. Now let's come to the second experiment of this paper, and this experiment was about the temperature deviation in a rebar depending on process parameters. For the test setup, we used a material as welding wire and substrate, which was comparable to construction steel. Furthermore, we used carbon dioxide as active shielding gas, and the printed vertical rebars had a diameter of 12 millimeters. For the experiments, we varied the waiting time between the welding with 10 seconds, 20 seconds and 30 seconds, and the temperature was measured at several measuring points on the surface of the rebar. Now let's have a look at the results. The diagram on the left shows the maximum temperature at every measurement point. Furthermore, the light gray line shows the acceptable temperature for mixture 1 and the dark gray line for mixture 2. In the paper you can find a further diagram that exhibits the mean temperature development depending on time after welding. The diagram in this presentation shows that the temperature decreased very fast from the approximately 1500 degrees Celsius at the welding point to the first measurement point 10 millimeters away from the welding point. Close to the welding point, the waiting time has a great effect on the temperatures. However, the further away the measurement point is to the welding point, the lower is the effect of the waiting time. From a distance of 70 mm, the waiting time is no longer decisive. Let us now conclude the main results of the temperature deviation measurements. The first point is that the temperature values of 50 degrees Celsius and 70 degrees Celsius are not significantly affected by the waiting time between the deposited layers, and between the welding point and the particle bed, a distance of at least 62 to 66 mm for mixture 1 and 82 to 84 mm for mixture 2 is recommended to ensure adequate penetration of the cement paste. However, for a decrease of the distance between the welding point and the particle bed, as well as to accelerate the production process, an additional cooling has to be implemented. After looking at all results of the feasibility study, we are quite happy that we can conclude that the combination of both methods is really possible. So what are the next steps? First, we want to determine the strength of the printed reinforcement. Furthermore, we want to determine the evaporation of the water within the cement paste at high temperatures and its impact on the characteristics of strength and durability. And finally, we want to design new materials as well as material combinations, and we want to implement different cooling as well as water storing strategies. Last but not least, we want to thank the German Research Foundation for funding our project and many other interesting projects within the Transregio 277, Additive Manufacturing in Construction, the challenge of large scale. Finally, let me also thank you for your attention, and I'm looking forward to your questions.